An important topic for us to talk about is what's known as Fourier Analysis. So, Fourier Analysis is whenever I have a periodic function, or at least a quasi-periodic function, something that's kind of well-behaved over a certain range, it can actually be approximated as an infinite sum of sinusoidal functions, which are all put together to create an overall function. So what does that mean? So basically what it is it's, sine responses and cosine responses, so harmonic oscillations, which are happening, which then you superimpose on top of each other, and then some of these are going to cause constructive, some are going to cause destructive interference, but overall any type of periodic function can be reproduced in terms of this sum of cosines and sines. Now, this video I'm going to split up into kind of the theory. I'll do a quick example to kind of see how this works with the standard type, and then we'll do an example that you would see in physics. Really has nothing to do with harmonic oscillation, at least in this case, the example we're going to look at. But it's something that you'll see a lot, which has to do with conductivity of temperature through some sort of solid rod, which is also known as the heat equation. But you'll see that in some of your engineering type classes. But again, the point of Fourier analysis is anytime you have some sort of function which is periodic, so periodic function, over some range of, say, from minus L to L, then what you can do then is you can rewrite the function as f of x then is equal to some coefficients a over 2, right, plus then the infinite sum n equals 1 to infinity of then a n cosine of n pi x over L plus some b n's times sine of n pi x over L, where a0, an, and bn are what are known as the Fourier coefficients. So these things are defined as a0 is the integral from minus L to L of f of x dx. An then is equal to 1 over L, integral from minus L to L of f of x cosine of n pi x over L dx. And then finally, bn is equal to 1 over L, integral from minus L to L, of f of x sine of n pi x over L dx. So again, anytime I have a quasi-periodic function, or at least a periodic function, which is periodic over the range in x, in this case from minus L to L, the point is that we can take a superposition of these sine or cosine or these wave disturbances, superimpose them on top of each other. Now again, the point of this is once I have particular types of frequencies, some of those frequencies will constructively interfere, some will destructively interfere, which will allow us to be able to create new waves, and then eventually by superimposing an infinite sum of all these things on top of each other, this will then reproduce the actual type of function that we're actually looking at. Now, here, the fact that this is a cosine and this is a sine actually comes from the fact that we're looking at the orthogonality condition of the sines and the cosines. I'll write that out in just a second. But the point of why we usually use this and why it's actually effective and why we actually use this as opposed to the original function is that it turns out that these Fourier coefficients, the a0, the n0, and the b0, or the bn's, are piecewise integrable and piecewise differentiable, which basically means that each one of these coefficients are independently integrated and independently differentiated, which means that when I write this out as a sum, instead of having some complicated integral that I have to do based off of the original function, all I have to do then is integrate each one of these guys term by term. Okay? Now, since each one of these coefficients depends on the actual original function, for different functions that I'm looking at, these different an values and these different coefficients are going to be different depending on the different types of functions that I'm looking at. Now, depending on the type of function that I'm looking at, a lot of times, a lot of these coefficients will end up being 0, but in general, these coefficients, at least the an's and the bn's, are going to depend on the value of n. So that means that the amplitude of the oscillation will be dependent on n, so they'll all have different types of amplitudes depending on which value of n that I'm actually looking at. All right. And again, like I said, this actually comes from the fact that the sines and cosines actually satisfy what's called the orthogonality condition. So let's write out what the orthogonality condition is real quick, just so we know where this comes from. So if I have the integral from minus L to L of cosine of n pi x divided by L times cosine of m pi x divided by L dx, this is equal to L times the what's known as the Chronicle delta function, mn, which basically means that Chronicle delta function, I think we talked about this in class, but if we haven't, I'll talk about it now. All this means is that this thing is either 0 or 1. It's 1 when m and n are the same, and it's 0 for anything else. So if you want to think about this in terms of a matrix, the matrix basically is that what? This would be a matrix with all 1s across the diagonal, and then everything else would actually just be 0, if you're more familiar with matrices. But again, all this means is that this thing is equal to L when I have cosine squared of n pi x. Because in this case, n must be equal to m, so that would give me a cosine squared. So that's equal to 1, or L in this case, and then 0 for anything else. Same thing's true for sine. So I have integral from minus L to L of n pi x with a sine. Sine of m pi x over L dx. This is also equal to L mn. So again, this is equal to L when m is equal to n, 0 for anything else. And then if I have the integral from minus L to L of sine of n pi x over L cosine of m pi x over L, this is simply also always equal to 0. Now, the reason for this is that because sine and cosine are orthogonal to each other, and we know that's because sine and cosine are shifted from each other by 90 degrees. So these things actually create a basis, and this basis is an orthogonal basis, just like your x, y, and z, or I hat, j hat, k hat, all that kind of good stuff. But again, just to kind of reiterate, the usefulness of this is the fact that each one of these terms, then, when I write it out as an infinite sum, are individually integrated and individually differentiated, which basically just means that, again, instead of working with the original function that I want to work with, so again, if I'm doing something like signal processing or signal analysis, where I'm working with a square wave or like a Sawtooth wave or something like that, if I write it in terms of the original function, doing these integrals and doing the processing is going to be something which is very difficult. So as opposed to doing that, it's a lot easier to do the Fourier expansion or the Fourier series. In this case, determine what each one of these coefficients are, and then simply do a term-by-term integration, which is a lot easier to do and is a lot more efficient to actually do it that way. Typically, if you're doing something with signal processing, you're doing something slightly different. In those cases, a lot of times you're using what are known as fast Fourier transforms. That's similar to this, but it's over a discrete range. So you're actually not doing an integral, but you're doing a sum. And it can get a little more complicated, but in that case, what you're doing is you are doing a transformation. So basically, like we just talked about, you're transforming your function from one domain into another domain. So from one space to another space. Typically in those cases, you're going from a time domain into a frequency domain, or from a frequency domain into a time domain. But let's not get caught up in there. That's a little bit beyond what we're talking about. So let's kind of look at an example. So the example we're going to look at is what's known as a Sawtooth Wave. So the Sawtooth Wave is, we're going to say that our function f of x is simply equal to x over the range of minus pi to pi. Okay. Which basically means in this case then that L is going to simply be equal to pi. Right? So what does this mean? So the Sawtooth Wave basically means that what, if we plotted our function f of x versus x, then from what, minus pi to 0, this thing then is going to be here. Right? And then this thing is going to come up, and then jump to here, and then it's going to come back down, and then jump to here. So this is going to be pi. This thing's going to jump back up to here. This is going to be minus pi, and etc. So this is what we call a sawtooth wave. So we get these beautiful things going on here. So what we want to do then is approximate this function using our Fourier analysis, and then determine what does this thing look like in a Fourier expansion, which basically means we have to go through and determine each one of those different Fourier coefficients, put all those things together, and then we'll find the Fourier representation of this. So let's start off with A0 first. So A0, again, we know is equal to 1 over L, integral from minus L to L, simply f of x dx. So let's put in our values here. So this is going to be the same thing as 1 over pi, integral from minus pi to pi of then x dx. And I'll talk about something with this in just a second. Let's do this integral. It's going to be the same thing as 1 over pi times x squared divided by 2, evaluated from minus pi to pi. Well, if I put this in, it's going to be the same thing then as 1 over pi times pi squared over 2 minus pi squared over 2, which is then simply equal to 0. Okay? Because in this case, I get a minus pi squared, but minus pi squared is positive, but I get this extra negative sign from subtracting those two terms, so this guy is simply equal to 0. Now, here we could have seen that this was actually true, and we could have seen this was true because of what? Well, we would know this is true because x is an odd function, so if I integrate over an odd function, the evaluation over the integral of the odd function over some period, or in this case I'm integrating over the period, has to be equal to 0. Okay? So the other way to think about this is what? So here I have x, right? So x looks like this. So in this case, if I integrate from minus pi, which is this location, to pi out here, what I know is that the area enclosed here is exactly the same as the area enclosed here, which means the average between those two is simply equal to 0. So if I integrate any odd function over the range of the period, the evaluation of that integral must then be equal to 0. So using that, that'll allow us then to determine what the ANs are automatically. And let's talk about that. So if I do that, so let's look at the ANs. So the AN then is equal to 1 over L, integral from minus L to L, f of x times then cosine of n pi x over L dx. So let's plug this in. So this is then 1 over pi, integral from minus pi to pi, of then x times cosine of n pi x over L dx. Well, in this case, again, I know this is an odd function. This is an even function. But if I take an odd function times an even function, that gives me an odd function. So overall, this entire function is odd. So again, if I integrate this function over the range of the period, this is simply going to give me 0. So automatically, I know all the ANs are also 0. Now I don't have to do integration parts and figure out what this thing actually looks like. So just save myself about 5 minutes, maybe. So good. Or at least save me some typing in the Mathematica, so that'll work as well. So finally, that leaves the BNs. So the BNs, again, are 1 over L, integral from minus L to L, then f of x times sine of n pi x over L dx, which is then equal to 1 over pi, integral from minus pi to pi of x sine of n pi x over L dx. Now in this case, I have an odd function times an odd function, because remember sine is an odd function. So if I have an odd times an odd, that gives me an even, just like an even times an even gives me an even function. So in this case, it's not going to give me 0. So I actually have to do this integral. So let's actually write out this integral. So here I'm going to use integration by parts, but I'll basically skip and I'll write down some steps here. So this is going to be equal to minus x over n pi times cosine of nx, right? Because in this case, actually if I put in the pi here, I think I should have, the pi actually cancels. Evaluated then from minus pi to pi, minus 1 over n pi, integral from minus pi to pi, then cosine of nx dx. Okay? So here, like I said, I'm using integration by parts. So here I'm setting u is equal to x, and then dv is equal to sine of nx dx. So that is this guy. Good. So let's actually write out this integral. So this guy is going to give me a minus 1 over n squared pi sine of nx evaluated from minus pi to pi. But sine evaluated at pi is 0. Sine evaluated minus pi is also equal to 0. So that whole entire term is actually gone. So we can ignore that term. So good, so finally, plug this in. So this is going to give me a what? Now remember, one thing is that cosine of negative n pi is the same thing as cosine of n pi. So actually those two terms are the same. So finally this is going to give me a negative 2 over n times then cosine of n pi. Now from here, we can then say that what? Cosine is then what? So this series here, remember bn's are starting off with 1. So cosine of 1, so cosine of pi is negative 1. But then for 2, cosine of 2 pi is the same thing as cosine of 0, which is positive 1. So this thing is actually either going to be plus or negative 1, depending on the value of n. Okay? And again, since I'm starting off with n then is equal to 1, this thing then is going to be equal to, I'm going to bring in that original minus sign in from here, so this is going to be equal to negative 1 raised to the n plus 1 times then 2 divided by n. So this is my coefficient bn. So good, let's plug this in. So what this says then is that's what? A0, an are both 0, so the only non-zero term I have is then bn, which means then that's my Fourier expansion of f of x is then simply equal to the sum n equals 1 to infinity of bn times sine of n pi x over L, which is the same thing then as the sum n equals 1 to infinity of negative 1 raised to the n plus 1 times then 2 divided by n times sine of, actually pi, so just nx, I forgot. L is equal to pi. So good. So good. So here, to represent the Sawtooth Wave, I simply have to add all of these sines and cosines together. And again, I've actually done this in the notes, so I plotted out in the notes a few values of these in Mathematica. So I plotted out the first Fourier coefficients, and then added those together, as well as put in the Sawtooth Wave. Actually, no, I drew the entire, this is the square wave. Not the Sawtooth Wave. Why did I do that? Oh well, that's fine. So, sorry, x, this thing should have looked like what I drew back here. So this would be minus pi. This would then be pi. So this thing should actually look like this. And then drop down and then do this. And then same thing over here. So this is the Sawtooth Wave. Sorry. I drew the square wave. I don't know why I actually did that. No, square wave would be, sorry, the original one is if I wrote something like fx was equal to a constant. So in that case, that would just be a constant over the domain. So sorry about that. And there would be two different constants for negative x and then for positive x. Or it could just be for some range. So 0 for part and then some non-zero constant for the other, just depending what it is. But sorry about that. Anyways, so in this case, I plot out the first 4 coefficients, and then another plot, I'll sum them together as well as plotting these. And then what you'll see is even the first 4 coefficients, basically what happens is this kind of comes down and then starts to follow this path. And then basically does something like that, and then turns around and then comes back down. So again, as you take more and more and more terms together, this then will approximate this thing and actually match if I take an infinite sum of these things together. Again, the reason that we do this, again, is because it's a lot easier to integrate and differentiate these because we can do it term by term as opposed to the original function. It's a lot more difficult to do it this way, especially if it's a lot more complicated type function. So, we'll do in the next video is we'll do a physics example of this, which I kind of mentioned earlier is what's known as the heat equation, which basically in this case, deals with how temperature will then distribute itself throughout a, in this case, we're going to look at a uniform rod. So we're going to hold one end one temperature, hold the other end another temperature, and then basically we'll see how that temperature gets propagated down through the entire thing. And it's going to depend on basically these Fourier coefficients. But as I said, we'll do that in the next video. But for now, we'll finish here.